It's time to get started. So I'd like to welcome everybody to the first Vamos of 2023. And we have a great one to kick off this new sort of season. So it's my pleasure to introduce Hartmut Häffner from UC Berkeley. Hartmut is best known, I think, for sort of developing and demonstrating many of the basic ingredients that are required for quantum computing with trapped ions. But I think what I most admire about Hartmut's research is that it's actually incredibly diverse and creative. It goes beyond that very important work to also a lot of kind of very really kind of exciting and different ways of doing things, like coupling ions with just a wire made of normal metal, or testing whether or not when you actually exchange two fermions, you can really directly see Fermi exchange statistics. Or even doing precision sort of tests of fundamental physics, like a version of the Michelson-Morley experiment, but using, instead of an optical interferometer, sort of the electron wave function itself. So these are really beautiful experiments, and they're spread a whole range of different fields almost. And today we're going to hear about something I wasn't even really aware that Hartmut was working on. So I'm very excited to hear the talk. So please take it away, Hartmut.
Yeah. Yes, thanks, everyone. Yeah, this is really fantastic, this series. And yeah, thanks, Shimon, also for the kind introduction. I think I deserve not half of net credit, but yeah, I'm going to talk about today towards trapped electrons for quantum information. And yeah, so maybe the question basically, a provocative question here is, are electrons the better ions for quantum computing? But maybe we should remind ourselves that actually one can also do much more with trapped electrons. And I will talk maybe a little bit about that. So yeah, as I mentioned, the motivation is, are electrons the better ions for quantum computing? And after motivating why this could be the case, I will speak about our first effort in that direction. And basically the experimental step we have done is we have trapped electrons in a Paul trap. And this, then I will speak about the setup, how to detect the electrons in this system, and how to characterize the trap characterizations. And then I will basically go a little bit more in depth on how a trapped electron quantum computer could look like, and generally about the prospects and also the challenges. So yeah, let me basically zoom in. Let's accept that we want to build a quantum computer. And then the natural question arises, which technology? And there are many, many technologies. And so this slide actually is, I think, not even, I mean, it's maybe somewhat up to date, but there are many more approaches even what are on those slides. And I see actually at the moment, we have maybe three leading technologies. I would say we have superconducting qubits, Rydberg atoms trapped in optical tweezers, and trapped ions. And with those systems, actually fairly sizable quantum algorithms have been demonstrated. Now, I'm a trapped ion person, so I want to maybe talk a little bit very briefly about what's good about the trapped ions, and then maybe also some of the challenges. So if you think about realizing quantum information processor, trapped ions have a few good properties, and they are very well isolated from the environment, and that means the coherence is very high, and that means you can actually achieve very high fidelity operations. And single qubit gates, errors, one error in a million has been demonstrated. With 2 qubit gates, actually the record, I think, is at 4 errors per 10,000 gates. So that's pretty good and nearly good enough for what we need. There's also the other good thing is it's modular. So I can build this quote small module of, let's say, maybe 20 qubits, and then I can use photons. Actually, there's a typo, to connect them each other. There's also flexible connectivity, meaning I don't have to control, let's say, 10,000 qubits interacting all with each other, or having the potential to interact. That is probably unfeasible and will lead to lots of errors. and I can, by moving the ions around, I will speak a little bit about this, you can actually achieve a flexible connectivity. So if you want to connect two qubits, you can connect them and then you separate them and then they are like really separated. And yeah, module size of about 20 ions have been demonstrated. And then I mentioned already queers. But there are also some downsides. And so the control is optical of the ions and also the Rydberg systems, the atoms. So atoms are great qubit carriers, but you need to often control them optically. And the optical control technology is nowhere near as mature as electronic control techniques. But we need good control, and this is actually like scaling the systems. The main challenge is to control, and so there needs to be a lot of effort to do control better. And the other thing is that ions are somewhat slow. And what I mean with that, typical time scales, depending on what operation you're talking about, we're talking tens of microseconds to milliseconds. And even though on a human time scale, that's fairly fast, but for computing, it's not really that fast. And if you want to do, let's say, crack a 1024 qubit number, bit number, RSA code, you may need 10 to the 13, 10 to the 15 operation, whatever, and then you can see that the operational timescales matter. Of course, many of those gates would be in parallel, but still, it's not very helpful if your quantum algorithms ends after the universe ends. So, so here the motivation why actually electrons may be better to use than ions. And so I want to compare mostly to the trapped ion technology, because that's kind of the theme here is to replace the ions in an ion trap quantum computer with electrons. And the main property which makes electrons very attractive is that electrons are fairly simple, probably one of the simplest systems out there. And they are light. And with simple, I mean, they really have only one internal degree of freedom, and that's spin. And that spin can point either along or anti-parallel to the magnetic field. And they're also the lightest particle we can reasonably well control, I would say. So that makes them move easily, fast, and simple actually simplifies our control in terms of what things actually can go wrong. So the spin 1/2 system, I think, is the ideal qubit. You can really think about very high fidelity operation. There's no leakage out of the Hilbert space or computational subspace. And that can cause problems for quantum error correction. You can think about if you measure a qubit in a particular state and you find it in that state, it's great, you know it's in that state. But if you find it's not in that state, if you have only one other state it can be in, then you know it's in that other state. But if you have an atom, for instance, you don't know in which of the many other states it is, and that causes problems with quantum error correction. And we can actually hope to do all electronic control. And then, yeah, it's the lightest charged particle. Okay, so here's the idea in a nutshell of the whole talk, is to replace the ions in an ion trap quantum computer with electrons. And the hope is that we retain most of the good features of the trapped ion approach. For instance, the electrons are probably fairly well isolated, long coherence times, but at the same time remove some of its challenges. And the challenges I see are the optical control. So we hope to do all control electronically, and also speeding up operations, because the mass of the electron is about a factor of 70,000 less than, for instance, calcium, which we use in my lab. I want to point out that there are related efforts, or were related efforts. One was actually by the Schmidt-Kahler group, the so-called Kalo program, where they worked on electrons in panning traps. And also what I find personally very appealing is to actually use electrons trapped on films of superfluid helium. And I think that's a very promising technology if some of the challenges can be overcome there. So I'm really curious where people can push that approach. Okay, so coming back to electrons and replacing the ions, and the framework I'm going to use is the so-called QCCD architecture. So it's where we have think about many traps where ions are trapped at different locations, and we shuttle, and Quantinuum is doing this, is shuttle the ions around. And if we want to have two ions interact, we basically bring them together in the same zone, and then we shine in some laser light to get the two qubit interaction going, and then we separate them out. And that is basically this highly flexible connectivity, which I think will be crucial for successful quantum information processing, because obviously I want good connectivity, but I don't want any unnecessary connectivity, because then suddenly I get entanglement where I don't want entanglement, and then large decoherence will set in. I think this problem will get more drastic the larger systems we're looking at. These ideas were actually put forward in Dave Wineland's group, 1998, right after basically quantum information took off. And since then, people are working on it, and there's some quite nice successes by Quantinuum. And so the idea is to basically replace the electrons with, to replace the ions with electrons. So that's what I want to think about. And the features I can hope for, or I'm hoping for, is that we have all electronic operation. The clock speed would be order megahertz instead of kilohertz. Coherence times, hopefully more than a second. I don't see any issues. And the temperature the system would operate at is somewhere between, let's say, 100 millikelvin and 4 Kelvin, depending on what we need. And we will see later why. The advantages would be almost no lasers. And why almost, I will speak also about. And it's actually easy to think about interfacing with superconducting qubits at that point, and it's about a factor of 100 times faster. You can also compare to superconducting qubits, and there you have less stringent cooling requirements. The coherence times, I think, will be much improved, and a better and actually higher and more flexible connectivity. I can actually basically shape the connectivity while I'm computing, change that connectivity, and that, I think, very few quantum computing architectures have that ability. There's a catch, and 2 years ago, nobody, or 3 years ago, nobody had trapped electrons in a Paul trap. So this is basically what we wanted to go about. And so we want to go from ion to electron qubits. And the things which are changing is that, yes, we're working with microwaves only, but in order to trap the electrons, we need to go from megahertz, which we use at the moment, or let's say 20 megahertz, 40 megahertz, maybe even 100 megahertz drive frequencies, to 10 to 20 gigahertz drive frequencies, because the electrons are much lighter. And to overcome the small mass, we need to drive the Paul trap much higher. And we will also need to go from room temperature to cryogenic temperature, which is also done with ions. And so the question for us was, how do we go about this? And we decided to not go fully for it. So we basically decided to make a small detour where we make our traps bigger and at room temperature first, to have an easier time to actually solve some of the issues. And the bigger trap actually allows us then to work only with a gigahertz or so. So maybe here's a good breaking point to maybe collect the first round of questions.
Okay, great. There are a few questions already. So one question is, maybe, of course, it's natural to present sort of the best aspects, but are there aspects of ions that you'll be missing in this architecture?
Yes, the optical connectivity. That's what
Yeah.
I'm gonna be missing, unless somebody has a really good idea. So for quantum communication, or let's say one has to then think differently about distributed quantum computing approaches. Yeah, that I would say is the biggest, what I would be missing. The other thing which I might miss is that a typical ion is not only a qubit, it has more states. and this can be used sometimes to one's advantage, but I don't really think that this is a big disadvantage, but who knows? Another one, yeah. Actually, there's another advantage is actually the cooling mechanism is totally decoupled from the qubit. So you actually don't need auxiliary qubits or so. You can cool while the quantum information is protected in the spin. So that's actually more an advantage. So, yeah.
Well, so maybe this leads into another question, but I mean, I guess so another person asked, you mentioned on the first slide a coherence time for ions of 2 hours. Is this referring to the coherent single particle evolution of a hyperfine qubit, or?
Yes, exactly.
So will you miss having nuclear spins, I guess, with lower magnetic moments and?
Yes. Yeah, but I don't think it's a big issue because the error rate in the end will be determined, in my view, totally by the operational errors. So let's say, I mean, we can call ourselves lucky if we will be able to operate, let's say, with 1 error per million, somewhere on that range, and then quantum error correction circuits actually will work very well. And what that means is I actually need only a gate time to coherence time ratio of 10 to the 6. So if I have 1 second coherence time, which is actually, I think, I mean, has been demonstrated with Zeeman qubits who have the same magnetic moment as the electrons in a room temperature setup, then I have already that ratio of 10 to the 6. And then in a cryo environment, I can shield the external magnetic fields probably much better. So I think this 1 second is actually a lower bound for what is achievable with trapped electrons for coherence time. So I don't think that this is a big issue. But yeah, it is definitely a difference.
And then maybe last question, and maybe you'll address this later on, but for those of us who are not familiar, can you say a little bit about what 2 qubit gates will look like in this architecture?
I will I have a slide on exactly how this actually would look. Yeah.
Okay, great. So maybe then we can move on for the time being.
Okay, good. So yeah, I will speak now about how to trap electrons, and I want to actually complement the introduction by saying that there are also other things you can think about when you trap electrons. For instance, Dima Butker is interested in trapping electrons and protons at the same time, and you can do that in a Paul trap. So you need to trap the electrons in a Paul trap to have them recombine and produce antihydrogen. Okay, I guess you would trap then positrons and antiprotons, but or plasma physics applications, or maybe. Yeah, maybe I want to leave it at that. So there may be other applications actually of trapping electrons in a Paul trap. So what do we need? We need a trap, we need a source, and we need a detector, and that's what I'm going to talk about. So I first want to talk about the electron trap, which is a Paul trap, and the typical layout is that we have, maybe I take now a cross section. We have a typical quadrupole trap where the black ones are DC or ground electrodes, and we apply AC voltage to these RF rods. And we use a different geometry, or slightly different geometry, where basically we use PCB boards, and this will turn here into the radio frequency electrodes, and the DC, the ground will be at the bottom and the top, and they can kind of see that this generates a very similar potential. And that's basically what we do. And then the hope is that we trap electrons in the center. This gives you some idea about the scale. So this is millimeter sized. So this is not 100 micron. That's what one would use then for maybe quantum computing applications, but we decided to go for a bigger trap first. And so it's some Rogers substrate, which has very good microwave properties. And the thickness of this center RF electrode is 200 micron. That's the smallest, and everything else is millimeter sized. Yeah, the trap potential, we are thinking about 1.6 gigahertz applying 90 volts. And then you can calculate what we call a pseudo potential, which is the effective potential generated by this AC field, which is applied. And here are cross sections, and you can see in the y direction, which is this direction, it's fairly harmonic, and the x direction, it's looks a little bit different, but it's still a pretty symmetric and deep potential. So we're talking nominally about order of electron volt, which corresponds to 11,000 Kelvin. So it's a fairly deep potential. Okay, the layout. So this is now a PCB board, and the electron trap will be here. So this is the slit in the center here. And this snake thingy here, that's the resonator we use to generate 90 volts or 100 volts at 1.6 gigahertz. There's a coax connection here where the about 5 watt of power comes in, is transmitted through, and it excites this quarter wave resonator here on this side. It's almost a quarter wave resonator. And then the trap here is actually on this side. And that's where we need then the DC electrodes to actually make sure that the electrons are then trapped in the in and like up and down, so vertically and in and out of the plane. But in the horizontal direction, we need to trap the electrons, and this is done then with these DC electrodes, which basically are on this boards at the top and the bottom. So you can see here the DC electrodes and the DC electrodes here on the underside, so you can't see them. And then we just use some nuts and bolts to actually put things together. And so this trap maybe cost, I don't know, about $100 or so. So it's not really particularly expensive, and yeah, fairly easy to fabricate, not by us, but by the company. So, and when we have this trap, we put that into a vacuum chamber. So we're talking about UHV, and using about 5 watt in terms of RF power, which is coupled into this system to generate then the trap somewhere here in the center. Okay, so that's the trap. Now we need to think about the electrons. We need to produce electrons, and when you think about it, it's actually not that straightforward, because let's assume for the moment, which is wrong, but maybe to some extent still correct, the Paul trap as a conservative potential. And if you create the electrons outside that potential, well, it rolls into the potential, but there is no real cooling mechanism, and there's especially no cooling mechanism which acts on a nanosecond time scale or tenths of nanoseconds, because that's really the trap frequency to actually cool them fast enough. So how do we get the electrons into the trap? So we kind of need to create the electrons inside the trap with low enough energy. And I talked that the trap depth is order of 1 electron volt. So you need to create electrons with an EV or less inside the trap, where there's presumably only vacuum. So it's kind of very difficult to think about how to achieve that. And the solution we came up with is using photoionization. So what we are doing is the exact same thing as what we are doing in our ion trap experiments. We send neutral calcium into our trap from an oven. There's maybe an energy of 600 Kelvin. So it's like 50 milli-electron volt, maybe 100 milli-electron volt. And then we tune our lasers into resonance with the 2 transition, or with the S to P transition in neutral calcium. And then with 390 nanometer, we go into the continuum, just above. And then the electron would be liberated. The cool thing is, well, that calcium atom, yes, has an energy of 50 milli-electron volt. And if you generate the electron with just a little bit more energy than it needs to be actually liberated, that electron carries only 1/70,000th of that energy, because, well, it has the same velocity as the calcium atom, but it has only 1/70,000th of the mass. And that's how you generate very, very cold electrons, how you can generate very, very cold electrons. So we do this by putting an oven here. So let me show you the oven. So this is where the oven is. It's a stainless steel tube which is filled a little bit with calcium, and then this tube is heated, and then the calcium comes out, collimated, and basically goes through the trap here. And then we shine in laser light perpendicular to it so that we have good spectral resolution, low Doppler line width, to actually excite the electrons, to excite the electron and then liberate it from the calcium. So here's a picture of this process. So you can see the calcium beam illuminated by the photoionization laser light. Good. So that's creating the electrons and presumably trapping in the in this structure, but we need to also verify that they are trapped. And for this, we need to detect them. And the way we detect the electrons is by extracting them from the trap and shooting them onto a microchannel plate. So we have, we apply some voltage pulses, order of 10 volt, to this one of the plates, one of the DC boards, to basically pull the electrons out and shoot them out, and goes through a mesh onto a microchannel plate. And so they are fairly large voltages, but they are far away, and then we can count them. So they go onto the, for those who don't know how a microchannel plate works, think of many photomultiplier tubes, and we use then the same mechanism. So let's put things together here. So here we have the microchannel plate where we then extract actually the electrons out. Here's a real picture of how this looks. So outside the vacuum chamber, this is the trap, the PCB trap. Here's the mesh. Here's the microchannel plate, and then this is how it looks when it's in the vacuum chamber. This was actually a very fun experiment because it was really low budget. The spot we found was underneath the desk, and so this is the whole apparatus. There's a vacuum chamber which we had lying around, and then this is the optics we need to generate the electrons. We can maybe later talk about how this may actually be then look in an electron quantum computer. Down here is a pump, and then we have some electronics. I would say that 80% of that electronics came from the trash. We are fortunate to be right next to shipping and receiving, where people dump their old electronics, and it's really like, for those who have been long enough in the field, like experiments were done in the maybe 70s or 80s, and so it's kind of fun to do experiments. So there was no computer involved. Now we have computer control to do better experiments, but at the time, just pulse generators and synthesizers and power supplies and stuff. Okay, so here's the measurement protocol now. So we this is a cycle. So to give you an idea, a typical cycle lasts about 100 microseconds. So we have the light to excite the calcium to the first excited to P state on all the time, but then we pulse the light at 390 to actually generate electrons during the loading cycle, which is order of tens of microseconds. And then we just wait, or we do something to the trap, and then in the end we read out with a short pulse. And you can see this here. This is here now the cycle is only 20 microseconds. So we load here, and you can see that we detect electrons during the loading sequence, but only very few. So this is blown up by a factor of 200 as compared to the actual detection of electrons. So on this axis, we have the detection probability per 1 nanosecond bin. And this is time. And you can see that over 20 nanoseconds, we see electrons arriving, and then this gives you some idea that we are detecting per cycle on the order of maybe 1/10 of an electron. But you can see that the signal to noise ratio is really big. So it's like during loading, we see only 1/100th or so of the electrons we then actually see when we look for them after they have been trapped. And so this may be already convincing in that we have trapped electrons, but we can do a few more experiments. For instance, we can wait for longer and then we record how many electrons we actually detect. So this should be maybe not the average number of electrons trapped, really average number of electrons detected. And we can see that we can load more and more electrons as we wait longer and longer with the wait time. We can also measure the lifetime of the electrons in the trap. So this is the wait time, how long we wait after loading. And this is actually an interesting shape we have not yet fully understood. But the first thing I want to say, this is a double logarithmic scale. And we load on average, let's say 1/10 of an electron. So it's not a many electron effect that we basically, they collide and then leave. It's really a single particle effect. And basically there are two decays here. There's one decay which doesn't quite look exponential, but has a characteristic time scale of 10 milliseconds, where we lose the electrons. But then there seem to be some electrons, and this is way above our background noise, which stay in the trap much, much longer, seconds, and then we stop measuring because it's just very tedious to measure longer, and they stay longer. And the question is kind of, why are there two different types of electrons, ones which drop out of the trap relatively quickly and others which stay in the trap very long? And we believe that this has something to do with the chaotic phase space of a Paul trap. And we need to remember these electrons are not cooled. They are inserted into the trap at a more or less, well, not arbitrary, but some relatively large region. And then they are in the Paul trap, and then they may leave, for instance, because they are in the chaotic region of the phase space of the Paul trap. Other experiments we can do is we can apply electric fields oscillating, presumably in resonance with the motion frequency of the electrons, to see whether we can kick them out. And this actually is really happening. So here we have the excitation frequency on the x-axis, on the y-axis, the detection probability, and we can see it's mostly flat except for two frequencies which match our predictions for the axial and the transverse frequencies. We can also crank up the power, and then we see, for instance, the axial ×2 and so forth. And yeah, I think those are all high harmonics of the axials, or could be also a sideband of the transverse motion. So this makes a lot of sense. And it's very similar actually to what we see with ions if we do the same experiments with ions. I think that is another good breaking point here to answer questions.
Great. So we do have some questions. One that came just as we were finishing the last question session was, are electrons more susceptible to anomalous heating than ions?
Yes and no. So electrons are lighter. And so with small electric fields, you can accelerate them more. But on the other hand, the trap frequency is much higher. So the energy scale is the relevant energy scale is higher. And typically you have 1/f noise. And it turns out when you look through things, mathematically, the impact on the quantum gates turns out that those effects nearly cancel each other. And so my answer to it, the simplified answer is they are the same, have the same susceptibility. But if you take an electron and put it at the trap frequency of 1 megahertz, it would be just horrible to work with. But since we are planning to work at 100 megahertz, a gigahertz, yeah, it's actually the same in terms of impact.
Great. Another question is, do you know what the sort of quantum efficiency of your electron detection is?
Oh, now I need to. I mean, it's fairly high. I would say in the 50%, maybe 70% regime. Just try to think how we actually quantified that. Sorry, I do not remember. I think I need to read our paper. I do not remember. Maybe we use the numbers from the supplier, what we use there. But then there's also the question of basically how likely do we get them? on there, but we did some simulations there, but I guess probably from simulations and to specs, and they are on the order of, yeah, detection efficiency 50-70%, I would say.
Another question is, if you wanted to, for sure, get only one electron in the trap, given that you have a beam of presumably more than one atom at a time, how could you guarantee that, or what would you do?
Yeah, so what in these experiments, I think it's nearly impossible. For quantum computing, we need a different detection mechanism, and we need a non-destructive detection mechanism, and I will speak about that. And then you can tell, okay, now I have one electron, and now I stop loading. And then we need also methods to separate electrons, and then presumably you have a Coulomb crystal of electrons. You can separate then out one electron. So that's basically sidestepping the question, I would say. But when one thinks then about quantum computing, yes, it's crucial that we work with a single electron, but then we get also the control and measurement capabilities, which would allow to really, make that then happen.
Okay, and then one question from the audience, just a clarifying question, I guess, is what exactly do you mean by saying the phase space of a Paul trap is chaotic?
Yeah. So the trajectory in a Paul trap will. Okay, so if you're so typically when we give talks, the Paul trap people, they talk about the pseudo potential, and even assume that's a harmonic potential. And so the trajectory is very regular and just described by a set of harmonic oscillators. And that's all fine if you have laser cooled ions, which sit right in the center, and the wave function is 10 nanometer and the trap is 100 microns big. What's happening then as the amplitude of the particles get bigger, it experiences anharmonicities of the trap potential, but then also the drive frequency becomes relevant, because the center of the Paul trap, there are no electric fields, but this is certainly, and also not from the AC field, you're working only using the field gradient, but once the amplitude becomes bigger, then there is a driving of that electron motion because of the radio frequency field. And then you can look at the trajectory of these particles, and then they become the trajectory becomes easily chaotic, because you have this. First of all, you have anharmonicities, and secondly, you also have this driving frequencies, which actually can pump energy into the system and really kick out your electrons. And you get what's called nonlinear resonances. So, for instance, if 5 times the radial trap frequency plus 2 times the axial frequency matches the drive frequency, then basically one photon absorbed from the drive can basically create then 5 radial phonons and 2 axial ones. And this way, then there's a heating mechanism and removes the particles from the trap.
Great. Okay, I think that's probably a place we can move on with the talk and save the rest of the questions for the end.
Okay, good. So yeah, the vision is really a QCCD-based trapped electron quantum computer. And now the question is, what do we need to make this happen? And when I entered the field, the DiVincenzo criteria were a big thing. And so I'm using the DiVincenzo criteria to see whether this is feasible at all. And here they are. We need a scalable physical system with well-characterized qubits. So the hard bit is actually not really the well-characterized qubits you really need, but it needs to be a scalable system. And I think the QCCD architecture is a nice example of where this is the case. Well, the electrons are well characterized, so I think there's not too much to say more about it. Of course, with scalability, the devil is in the details, and you have to look very carefully. There are many concerns here. If you have such a large array, you actually need to drive all these traps. You need to supply AC voltage. There will be power consumption issues, especially if you're cryogenic and so forth. but I think in general, the idea itself, I think, is a fairly good example of being scalable. We need to initialize the qubits. And this is actually something which is hidden in the other criteria. If you can read out the state of a qubit, and if you can do a single qubit operation, you already have solved the initialization problem. And what I mean with this is, let's say you have a qubit, you don't know whether it's 0 or 1, and you want to initialize it in 0. What you can do is you can read out the qubit and you can determine, oh, is it 0 or 1? If it's in 0, I don't do anything. If it's in 1, I basically do a spin flip. So in that sense, that criterion is already fulfilled. Of course, it's nice if you can just do optical pumping, then you don't need complicated logic. Well, logic is not complicated, but you don't need to implement any logic. You just do optical pumping. You're done in a microsecond, great. But yeah. But that's basically the strategy I propose for trapped electrons, because we need to read out anyways, and we need single qubit operations. Long coherence times, I think there's not really too much to say other. It's a single particle in vacuum. If you control the magnetic field, I don't see many issues there. That's the coherence time of the qubit. We need a universal set of gates. So we need to be able to do especially 2 qubit gates, and we need to read out. And those are the hard bits. And this is what I want to basically focus on now. And basically the short message is to use spin-dependent forces via oscillating magnetic field gradients. And many of you may know already that this is what's done currently also with trapped ions. But before I do this, I want to basically introduce you a little cartoon how actually we are envisioning things to look like. So we have a trap where we have something which looks like a surface ion trap, where we think about applying 20 volts at 15 gigahertz to provide the confinement of the electrons in the transverse direction. We have then DC electrodes to confine the electrons along the longitudinal direction. And then we have an electrode on top, because we don't really need a lot of optical access. We need only for the creation of the electrons, which could be actually somewhere else, and then it could be transported here. There is what I would call a pickup electrode. And the idea is the following. We also need to cool the electrons and detect the electrons. And the idea is that by connecting the pickup electrode electronically to the bottom layer, then if the electrons move, they induce a current between the 2 plates. So there's then a current flowing, and I can send this current over an LC resonator. And here are some typical parameters, 6 nanohenry and a picofarad. Gives you a resonant frequency on the order of 100 megahertz or so. And that resonance circuit is then in resonance with the current induced by the electrons. So the electrons induce, of course, an AC current at their motional frequency, and that current is sent over this LC resonator, which is in parallel and has a high impedance. What happens is then that there's two things happen. One thing which happens is that there's a voltage drop. So over this effective impedance or resistor, and that voltage drop can be amplified and basically would constitute a signal. You do a Fourier transform of the signal, and you see then a peak at the electron trap frequency. And this method actually, so this sounds totally fancy, but for the people who have a penning trap background, this is business as usual. That's what they always do. So you can detect electrons by just looking at the image count. For instance, Jerry Gabriel does this all the time. And you can then detect this, you can even count the number of electrons, because the signal strength has something to do with how many electrons you have. So that's one thing. The other thing which is actually happening, so this voltage drop which happens here has the opposite sign of basically the voltage induced opposes the motion of the electrons. right? So there's a voltage induced over the resistor. So that means there is a voltage over the trap electrodes, and that opposes the electron motion. And you can think of it that the electrons inducing that current, that power, that current is dissipated because it has a finite quality factor in the tank circuit, and that tank circuit therefore damps the motion of the electrons until the electrons reach the same temperature as the temperature of the electrons inside the tank circuit. So there's an imbalance of the Johnson noise, and yeah, that's the Brownian motion. The Brownian motion essentially of the electrons. And so this is kind of the idea to cool the electrons and also detect the electrons. And this technique is very well known for penning traps. And our idea is to use that same technology in Paul traps. And of course, there are unique challenges there, but we think that this is doable. So that would be the detection of the electrons themselves. That does not mean that we know about the spin direction, but it tells us we can measure, for instance, the trap frequency very well this way. So how do we now go about detecting the spin direction? And the idea is to use a spin-dependent force applying a magnetic field gradient. And we all know that if you have a magnetic field gradient and interacting with a magnetic moment, there's a force. And the direction of that force depends on the spin direction. So the idea is to have a magnetic field gradient which we oscillate with the trap frequency. So let's say the electrons have a trap frequency of 100 megahertz or 300, let's assume 100 megahertz. And I oscillate now the magnetic field gradient at 100 megahertz. And then there is a force, but the sign of that force depends on the spin direction. And that force is in resonance with the trap frequency. So let's say I start at with a very cold electron. The electron is excited into coherent state, but the phase of that coherent state will now depend on the sign of that force, and the sign of that force will depend on the spin direction. And this way, we encode the spin direction in the phase of the coherent state. And by doing a Fourier transform, Fourier analysis of the induced image current, I can tell the phase of that coherent state. And this way, we can then detect essentially the spin direction. So that is the idea. So are there maybe questions about the detection mechanism?
Yeah, there's a couple questions here. So it says in a traditional ion quantum computing architecture, the cooling can be turned off on and off lasers.
Yeah.
It seems like the cooling and the detection kind of will always be on, or I mean, maybe in a specific region. So is that okay, and how would that work?
Yeah. The first thing is it's mostly okay, because if we don't apply a magnetic field gradient, there's no coupling of the spin to the motion. But while you're doing this, you don't want this to happen, or at least you want to have the cooling smaller than this time scale. And the way to achieve that is to just change the trap frequency, because the efficiency of the cooling depends very strongly on the impedance of the attached tank circuit. And so you can tune essentially the cooling off to all practical purposes by just detuning the trap frequency outside the bandwidth of your resonator.
Maybe a slightly related question from the audience is, will the pickup electrode be affected by the AC field that you're applying to trap the?
Yeah, so there is definitely AC pickup, and there's definitely problems with the amplifier coping with that. So the trick will be to have good filtering, the right geometry, so that this pickup is minimal. There is no, so one thing people were or are afraid is, right, you have this strong AC field at 16 gigahertz. Will that somehow cause trouble in the electrodes so that they heat the electron at their motional frequency of 100 megahertz or whatever it is, or gigahertz actually for the transverse? And the answer to that, we know from trapped ions that this is not happening, because we can cool also, we can keep our ions also for a long time cold in trapped ions. So it's I see the main challenge here really on the electronic side. And yeah, so that's basically, yeah.
Maybe one more question. I mean, I guess you're probably coming to this still, but I guess the cooling obviously is not as you cannot cool as cold as you can get with sideband cooling in ion. As you said, you're equilibrating with your resistor, which is at some 1 Kelvin or something like that. Is that sufficient, or do you actually need to get down to lower motional, occupation numbers?
Yeah, for quantum gates, it's fine. So we calculate, I will show estimates of gate fidelities, and there we assume like a temperature of 4 Kelvin, so that would correspond to 80 quanta or something like this. And yeah, basically the decoherence is larger, but it's not such a big deal. But we thinking about, and we have an idea how to actually get to colder temperatures than that by using sidebands, so that basically, if we modulate the electron motion at a very high frequency, a sideband is created, and then we would be effectively cooling at a higher motional frequency. And so basically what matters is how many quanta does the tank circuit have. And if you use a tank circuit, let's say at 20 gigahertz at 1 Kelvin, you would have an expectation value of 1 quanta. So if you are able to couple the electrons to a 20 gigahertz tank circuit, you cool to an n bar of 1. And that would be a viable way to go there, to go to even lower temperatures. But for the gates, 80 quanta is fine. Where actually we see problems is having Coulomb crystals. So it turns out that around 4 Kelvin, the Coulomb crystal, we learned that only recently, forms in our simulations. So there is actually, I think, a weak point, but there are ways to get around this by, for instance, never putting the electrons into the same trap, because they are so light, you just need to bring them close to each other, and then you would never have to worry about this. But I would say, yeah, we need to yeah, there are things we can do, but I don't, yeah. Before we really haven't done some fundamental experiments, I think we just don't know enough where exactly there the challenges are. But yeah, we would like to get cold. Of course, we can always say, oh, well, dump that resonance circuit at 20 millikelvin in the Dill fridge and we will be fine. But we would like to avoid that as much as we can. I have never worked with a Dill fridge, but I'm not particularly keen on doing so. So if we can get away with, let's say, 4 Kelvin or 400 millikelvin, that would be great. So that's kind of what we are trying to manage.
Great. I think we can continue with the rest of the talk.
Good. So quantum gates, and the idea is very similar to the spin detection. And it's again using a magnetic field gradient which oscillates nearly with a trap frequency. Let's think now about 2 electrons, and you have a center of mass and a stretch mode. And let's think about now only that we have a drive which is fairly close to the center of mass mode of the 2 electrons. And on the right-hand side, we have 4 possibilities how the spin direction could be of the electrons. And now if we have the drive, and if the spin points in the same direction, let's say spin down, as in the top case, and I'm driving with a magnetic field gradient, you can see that you can excite that center of mass mode because both electrons have the same spin direction. And if we detune now that drive, and this is the same as what we do with the Malmö-Sørensen gate and other 2 qubit gates in trapped ions, if we detune it slightly from resonance, you excite the motion, and then after some time, which is 1 over the detuning, you de-excite the motion, but temporarily the electrons had a higher energy. And that basically means that there's a phase evolution and you acquire a phase. And that's happening if the 2 electrons have the same spin direction. But in the center, like here, there are electrons who have opposite spins. And then you can see that the force on them is in the opposite direction. And that means you cannot excite the center of mass mode. and that means you have no phase acquired. And what you have done to your wave function is the spins are never touched, really. They have the same orientation as before, but a phase has been accumulated, which depends on the two spins in the same direction. I get a phase. If not, I don't get a phase, and that's actually turns out is a phase gate and is universal for quantum computing. So that's the idea for a 2-qubit gate. We have simulated now various error sources, imperfections, what we expect to happen. And for these simulations, we assume actually that the electrons are at 4 Kelvin, or that they're cooled in a 4 Kelvin environment. And we think about the Bell state, the quality of the Bell state we can generate then with this. There are 3 lines always, and they have something to do with what kind of dynamical decoupling we do. So there's kind of a dynamical decoupling, it's called a Walsh sequence, done, which is also done for trapped ions. And on the y-axis, we always have the Bell state infidelity, and then we have 6 different decoherence mechanisms. There's motional heating, which has to do with what was talked earlier, what some people call anomalous heating. I call it rather electric field noise, because it's a fairly normal process, as we unfortunately learned. And when we extrapolate from the numbers known for trapped ions, we expect roughly an infidelity or an error rate of 1 in 10,000. And this is the most important error source we attribute. And actually, I should say, if we do, this is a conservative estimate. Actually, the heating rate actually should be at 4 Kelvin, more like well below 100 quanta. The motional frequency may not be as stable as we wish, so that leads also to an error, maybe depending on how much dynamical decoupling you do, but we expect there less than an error in 10,000. There may be very fast frequency noise that should not play a role. The gradient actually we apply is not necessarily homogeneous. That will also cause then problems with the finite temperature. Then we are also talking that error, range of an error in 10,000. And the field is not harmonic. That can be compensated very well. And the qubit decoherence really is I believe, not really relevant here. So this is basically an overview of what we believe are the most important error sources and our estimates of this. Of course, those are all estimates. We don't have the exact layout of the apparatus, nor do we have any measurements. So this is all speculation, but we believe that the errors can be pushed down into a regime where it's actually, yeah, better than what is existing in other technologies at the moment. So basically, I want to, or maybe other questions with respect to the gate before I start summarizing.
Well, maybe I'll ask a quick question. So do you have estimates for what the gate times will be?
Yeah, so the gate times should be on the order of 1 to 2 microseconds.
And then what about, I mean, sort of your readout and I guess as a result, state preparation fidelity and the times for that? Is there?
Yeah, so the time for readout, we think about 30 microseconds, and fidelities are order of 3 nines.
Okay, great. I think that's those are the only questions we have right now. So we can maybe move to the summary.
Okay, good. So yeah, talked about the DiVincenzo criteria, how they are fulfilled. We have something which looks scalable. We know how, we have ideas how to initialize them, how to read them out, how to do quantum gates, and so forth. Yeah, this is all, of course, happening with a large group. And I want to point out especially Clemens Matheson, who is now at Oxford Ionics as a postdoc, and Tian Yu, a graduate student who made the project working. We have another Izzy as a graduate student, and Neha and Alberto as postdocs. Master's thesis students, actually, Peter Tierley from ETH Zurich and Edith Houston from Greifswald. we have some sort of collaboration with Berger Hemmerling's group, or some sort of good collaboration. So we meet every week remotely. And Tyler Sutherland, who's now at U Texas, and together with Christy Beck, actually helped us with the theory. And we have also frequent discussions with Didi Leibfried and Daniel Slichter from NIST. I want to say that Keysight is really what gave us a little grant to actually get started. And yeah, I want to also point out that Nikos actually postdoc who actually thought first about trapped electrons in the context of connecting to superconducting qubits, and Pai Peng as a grad student, or was a grad student at MIT, and Tim is actually at Harvard right now. Yeah, thank you for your attention. And yeah, basically the short summary is we trapped electrons, and we're working on getting it onto the map on viable quantum information processing technologies. Yeah, thank you for your attention, and yeah, looking forward for more discussions, questions.
Yeah, great. Thanks a lot, Hartmut, for really excellent talk and very sort of exciting results. So let's see, I'll remind people they can ask questions using the Q&A or on YouTube using the chat function. But in the meantime, I mean, maybe I'll ask kind of an annoying question, which is what do you think the timeline is for scaling this up?
That's a good question. Let's say 10 years. We are hoping to have in a year to have trapped electrons in a cryostat, and maybe detected their presence with an LC circuit. But then, yeah, there are lots of things we have to learn. Yeah, so yeah, I mean, I think, yeah, it's a difficult question. Yeah, but I can guarantee that we won't have like, let's say, demonstrated 2-qubit electron quantum computer within the next 2-3 years, but I would hope so that we have done so in the next 10 years.
So there's a question from the audience. The phase gate you described, is that not more like a ZZ gate? And
yes.
ZZ is in tensor product of 2 poly Z gates. Yeah.
Oh, well, we call it like, yeah, it is a ZZ gate, and you would write it down as C tensor C. But it's really an entangling gate. And so I'm not really. Oh yeah, I'm not sure exactly what that question aims at, but if you complement it with single qubit Z operations, then you can turn it into a phase gate. And so I hope that this clarifies this.
Let's see. So I think actually there at the moment there aren't additional questions that I can see, unless I'm missing some here. But so I think we had a lot of questions during the talk. So I think we're right on the hour too. So I think we can probably call it there. But thanks, Hartmut, again for a really great presentation, very stimulating. And you know, I think the panel can feel free to hang out and chat and ask more questions as they'd like. But the last thing I'll say is I just want to advertise the next VAMOS talk in 2 weeks, which will be given by Andrew Ludlow from NIST on enhanced cooling and quantum control of divalent atoms for the next generation of optical lattice clocks. So we'll see you all then.
Cool. Thanks, everybody.
Yeah, thanks a lot.
Thanks, Hartmut.